Okay, good morning. So today we will have two lectures, one now and one in the afternoon, and we try to wrap up in the afternoon. What I want to do today is to discuss not the entire formalism, but some ideas of the post-Newtonian formalism. And let me start from this formula that we derived day one. This comes from the dimensional analysis of the quadrupole formula. R is the source, the radius, typical radius of the source that emits gravitational wave. H is, of course, the gravitational wave strain. This is the distance of the source. This parameter combining the mass and the size is called compactness or self-gravity. And this is V over C squared. And so we have argued that while we had used linearized approach on Minkowski to derive gravitational waves, and in particular the quadrupole formula, the prediction that this formula gives is that the gravitational waves are mostly emitted, or they are most significant when they are always there, but they are most significant when the source is very compact. So that would be this term, that maximum value of this term is 1/2, the Schwarzschild radius. The Schwarzschild compactness, so related to the definition of the Schwarzschild radius, and very relativistic. And we said that that formalism that we developed, actually, strictly speaking, would not apply in those conditions. Remember, there was, so this was a small velocity so this was from the linearized approach, linearized on Minkowski. And in particular, we had few hypotheses to derive this, that is a small velocity. And, well, a fixed flat background eta, which does not account for gravitational interaction. So this is essentially small velocity kind of is related to this term, and flat background is related to this term. So that very big, there cannot be big gravitational wave under this hypothesis, okay? So what we need, so this indicates that there's a need for a formalism that account for self-gravity. Of the source. Or strongly, of the source. And this would eventually describe things like, finally, neutron star and black hole that we know are the sources of our observation. Okay. And if you have self-gravity, this independence between the velocity and, say, the gravitational field is broken, okay? So in this case, the velocity and the gravitational field are connected. In particular, through the virial theorem, V over C, it's something like, so this term, it's something that is comparable, the order of magnitude to this term, okay? Which is, of course, as I said before, the Schwarzschild radius over R. Okay, so these are not anymore two independent things when you have self-gravity. And so the idea is to say, okay, what we could do, we could say, okay, we go progressively, and we still take a perturbative approach, but we have one parameter, which could be this or this, it doesn't matter, they are the same, okay? And we could try to look for a solution of GR in a perturbative solution GR that is an expression, that is an expansion in epsilon that is essentially this small parameter. So you can think of it as the ratio between the velocity of the source of the speed of light, or if you want, the gravitational potential. So formally you can write, this is the sup of GM CR 1/2, it's the square root, and we will assume that there is a source of matter that is compact, so that has a compact support and as smooth as we need. And in particular, that the component of the stress energy tensor have this relation with the small expansion parameter. This essentially says that the velocities, the typical velocity of the source, are a factor epsilon, the density, and the typical stresses of the source are a factor epsilon square, the density, the typical densities, okay? Okay, so how do we do it? Can we simply proceed in a way similar to what we did with linear gravity? Well, not really. So we need to take into account that we are in a nonlinear theory, and for example, that gravitational wave emission subtract energy to the source. Let me write it this way. It's not very precise, but we cannot simply prescribe equation of motion through this as an expansion in this parameter and afterwards calculate the gravitational waves, as for example we would do, I don't know, in electromagnetism. Okay, this is not possible because at every order we possibly have gravitational wave emission which subtract energy to that motion. So it's kind of loop, right? It's a kind of circular thing, which is what Einstein equations are. And another observation is that as we have learned yesterday, gravitational waves are sources at a given, say, Pn iteration, are sources of gravitational wave for the next. Okay, so these are the complications. Well, that you have, but this is just because you have Einstein equation, right? So what you say of Einstein equation is that the motion of this is generated by the curvature, but also that the matter generates curvature, and this is a kind of nonlinear relation. So how do we do it? Well, before telling more or less the main feature, let's say, of the actual formalism, let's write down some result that we already know, okay? So we know that at the Newtonian level, let me call it Newtonian order. What do we have? The Newtonian order, we have a metric downstairs, which is of this form. I will slightly change notation now, but this essentially is what we wrote down the second day. This is 1, so it's the piece of Minkowski, and U is essentially the Newton potential. Actually, this is minus, but it doesn't matter at this point. And this is actually the lowest order, so it is even weaker than the weak metric, because here I'm even taking the spatial part as just diagonal and flat. Okay, so this we know already, and this comes essentially from the weak metric. Okay, so the idea is that at least we have an initial starting point, and we can hope to iterate we have the starting point of the series in epsilon, and we can hope to iterate Einstein equation to find the next correction. And we can say even a bit more, just again, without having really lay out anything very detailed, we can say something more. So from here, as I said before, from here, T0I is something that is always order epsilon, this ratio, and as well, the other one is order epsilon square. And so you see immediately that if you have, if you use Einstein equation, or if you just look at the Einstein equation, you see that if the G00 at a given post-Newtonian order is something that is order epsilon to the n, this will be called n half post-Newtonian order. It doesn't matter, I will tell you later. Then the other component of the metric have respectively 1 order more and 2 order more. Okay. So what we have learned, just by this simple argument, that different metric component have different kind of order of expansion. And we can say even something more. And this is an argument that goes back to Chandrasekhar and Esposito Ferrese in the 70s. If we assume there is no gravitational wave, and this is true at the first orders, so it's definitely true at the Newtonian order, but it's true also at higher order, up to 2.5, as we shortly see, then the metric has a symmetry under time reversal. So T, for a change of T that goes into minus T, okay? What does this mean? This means that if there is no dissipation mechanism, the motion is conservative. Okay? This also means that V goes to minus V, of course, in these terms. And so what this means, or what this implies, is that if you look at this quantity for, if you look at this metric component, this implies that the G00 component and the Gij component, if there are no gravitational waves, they contain only even powers of epsilon. Okay? Whereas the other one can contain only odd power. So we can make a table and look at what we expect in the for the first post-Newtonian order. So I will write that I will use this notation: G component with upperscript n is a component of order e to the n. So we can write down what these components are at every Pn order. And I will tell later what I mean by the 0, 1 Pn or 2 Pn. So, but this means Newtonian, okay? So this will be 1 plus G00, 2. We see it there from our Newtonian starting point. There is no G0I, and this is a delta Ij. Then we can go to one order higher. So to one order higher, here I can have only even power. So this is epsilon to the 4th. The G0I is epsilon to the 3, which is odd. And the Gij now starts with a factor 2, with the epsilon, with the components of order epsilon to the second power. We can also continue this, say, to the 2pn, where still there are no waves. And of course, this becomes the G00 gets component epsilon to the 6th, G0I gets component epsilon to the 5th, and Gij gets component epsilon to the 4th. Okay. So this is the power counting for the first order of the series that we are looking for. And yeah, there's a notation thing, or yeah. One usually says that a correction order epsilon to the n, or if you want c to the 1 over c to the n, which is the same, it's called an n-half pn. Okay, so this is a convention, and yeah, many people nowadays use this. Okay, perhaps not all the books have this, or not all the old papers, but I think now more or less everyone uses this convention. So you can ask, where does the scheme break? Which means when gravitational wave appears, okay, this is a better question, but, and the answer is 2.5 pn. And a simple argument is the following. You can write down think about, let's think about an orbit, a system with, of two bodies that are orbiting, okay? So we can write down the energy of the orbit, which will be the kinetic energy plus the potential energy. You use virial theorem, and you get that this energy has to be of order minus 1/2 the mass of the binary times v squared, which means that the derivative, the variation of this orbit in time is something like minus minus mv v dot. And then you can say, well, if, yeah. Because this is 0.
Okay, that's just like a
yes.
strict result. So this is O of epsilon, which just appeared to be proportional to 0.
Yeah. And you can say here, okay, if the energy of my bound orbit, for instance, is changing, as you have calculated also in the last days, it must be for gravitational wave reasons. So you invoke this heuristic principle that is the detail balance, and you say that the variation in the orbital energy is minus the power that is emitted in gravitational wave, which we have calculated, and one of the formulas that we had in the last days was this, I think, where r is the radius of the orbit. So we want to lose the thing. And then, so this is the energy balance, okay? And again, it's an argument, okay? So it's not proof, but it turns out it gives the right result. And this gives you that v dot, so the acceleration is something for this argument that goes like gm over r squared v over c to the 5th power, okay? Which means, this is the result that we wanted, this means that this orbit starts to change because of gravitational radiation at order v to the c to the 5th power. So this means epsilon to the 5th power, which means 2.5 pn. This is just an argument, but it's true. So if you do the proper calculation, which is non-trivial, this is what you find. Okay. So essentially, this table, this power counting, is perfectly fine up to this order, and there is also, and here you would start to worry about what to do. Because I think I have a wrong, let's see. Let me see if I did it correctly. This result is correct, but now I'm thinking where this comes from. Sorry? You mean because you would count also this as it's an argument, so yeah. What you want to look at, it's this. But I'm worried if this power is correct, but I think so. Okay, so if that power counting is correct, and if we know the Newtonian order, what we may attempt is to go to 1pn. So to calculate the metric at 1pn, which is a useful thing to do. And so I tell you how one can do it. And this is a calculation that is described in Landau-Lifshitz. So the idea is that you start from Einstein equation in this form that we have seen last time, the first day, sorry. So you assume harmonic gauge. And you remember that in harmonic gauge, the equation was something like that. There is a sort of linear, well, it's not a linear part, but there's a box operator which contains the highest derivative. So this is not really linear because there is the inverse metric and so on, and the determinant, but, and this is the non-principal part that contains lower derivative, okay? So you start from there, and then you take all the nonlinearities, you take all, which I'm not writing down, but you take all the nonlinear parts, and you simplify that by using this, essentially this power counting. So usually the fact that G00 plus 1 is order epsilon square, G0I is order epsilon to the third power, Gij is, Gij minus G00 plus 2ij is order 10 to the power of 4, 8e epsilon to the power of 4. And also you use the fact that the time derivative of the metric in our approximation essentially can be are subdominant with respect to the spatial derivative, okay? This is an important thing because you can discard these terms, and physically this tells you that in the post-Newtonian theory, what you do is to discard or approximate in the retardation effect, okay? So it's something that we have briefly mentioned at the very first day. So you have in general a function of your, think about how we derive the quadrupole formula. You have a function of the retarded time, because this contains, you know, the causal physics that is inside here. But we have expanded in this time and truncated that expansion, okay? So you kind of eliminate this, you kind of expand in this effect, and this means that you're kind of neglecting the time domain part, the time domain variation in favor of the spatial part variation. Or if you want, your box operators can be approximated as Poisson operator, okay? So if you do this simplification to the equation, and if you use a variable for G00, which is not G00, but it's the log of G00, you can absorb the remaining nonlinearity, and what you find is that the 1pn equation are actually linear and have this form. Sigma is T00 plus the spatial trace of K. This is G0I C3 what is, no, this, okay, I have a mistake here, but there's a G, this is 0I. This is, what it is. I look what this is. Then, yeah. Sorry, I need to look a couple of coefficients because I'm not sure. What is it? 16 pi G, 16 pi G over C4. Okay, no, this is fine. Yeah. This is just that. So this is what you find at 1pn, okay? And the interesting aspect is that these equations are now linear. Okay? And it's because of this, because there's this trick that you can use the log variable and incorporate the nonlinearities there. So what does this mean? This is the stress. This is pieces of the stress energy tensor. Okay, this means you can integrate with Green function method, and essentially, if you calculate these two integrals, so sigma essentially, the whole solution at 1pn is given by the calculation of these two Green integral, which are the usual Green integral, where here it appears sigma, but this is just combination of the stress energy tensor, okay? And so under the hypothesis that the source is compact, under the hypothesis that the source is smooth, and so on and so forth, this integral exists. For a given, once you have specified the stress energy tensor, you can calculate it and plug them back in. And let me just write it here. So the 1pn metric has this form. Of course, for G00, you have to exponentiate to get the thing. And 1 plus 2v over c squared. Okay. Here is the metric that you have at 1pn. So just a note, these guys return over and over in this type of formulas, so they take name. Oops. This one is called the active gravitational mass density, and this is called the active gravitational current density. And the reason they take name is that it's not just rho, it's not just T00, it's this particular combination, which you see basically includes the pressure as well. So there's a pressure term here. And okay, this is just. And they return over and over in this type of expressions. Okay. So you have the 1pn metric. What you can do is to calculate the motion on this 1pm metric. So let's start here. And take, for example, n particles. Here. I'm not, okay. Let's say G1pn. Take n particles, the stress energy tensor, so particular expression of this T mu is 1 over square root of the determinant, or minus the determinant of G. Then you have the sum over particles. Particles are, delta functions. So you have the mass of each particle. You have the Lorentz factor of each particles, which you can write this way. This is gamma Lorentz factor. And then you have deltas. You have the velocity. And then you have the delta at the particle points. So the stress energy tensor is this, collection of delta, for n particle, this collection of delta functions. This is easy. This is not 1, because now we are in a 1pn metric, but this is 1 minus 4 the Newton potential. So if you want, this is, anyway, let's write it this way. And so you have basically everything to calculate the metric. To calculate the Lagrangian and the action. And this Lagrangian is called as a name from the people that propose it. This is the Einstein-Infeld Hoffman Lagrangian, and you can calculate it. I'll not show it completely, but essentially what you have to do is to solve, where are they? Solve these metric potentials, now plug in that T mu nu, okay? And then calculating, say, for all the particle except one, let's call it B, and then you can calculate the action for that particle, which is minus mc integral dt of this G mu nu, which is now the 1pn metric solved in terms of this V thing. And of course, the total action will be the sum over all these B particles, so all the particles of this S. And from this, the Lagrangian is inside that. From this, you get a Lagrangian and the equation of motion. And as you may expect, the Lagrangian is the Newtonian part. Kinetic energy plus potential energy of all these particles. So this is sum over A. So you get what you expect. G MA MB divided RAB. This is the Newtonian part, plus a correction, which is a long expression, and I'm not writing down, but this correction is as inside, just to give you an idea, terms that are like, there are sums, of course, and there are terms like MA VA to the fourth power. There are terms that are like MA, BA, RAB, VA square, VB square. So this is also velocity to the fourth power. And there are terms with three masses, A, B, C, RAB, RBC. Yeah, this way, okay? So there are a few terms. It's quite a big Lagrangian, okay? But it's still like this, and in particular, it's still invariant by time translation and rotations. For n equal to, sorry, because that's what I'm gonna do. So what happens for n equal to? So for a binary. For a binary, the solution to this equation of motion was given by Damour and Deruel. Two papers, I think the first was 85, 86. And they want to look, or they took n equal to, and they wanted to look at Keplerian-like orbits. So what happens, what are the changes, how the motion becomes. If you include these 1pn terms, what you find is that, well, you should go in the center of mass. I'm just catching how this calculation went out. So this is a difficult thing. Huh? You go in the center of mass. There are two conserved quantities, those that I mentioned before. So it's time translation invariant. So you have an energy. You can write it as an energy per reduced mass. And this starts like one, well, like the Newtonian and plus all the terms that are there. And you have the angular momentum conserved as well. So this also starts like the Newtonian, and then you have more terms. Okay, but these are conserved quantity in the 1pn motions, so which you can use to write down some equation, which again are similar to, say, the equation that leads to Kepler orbit. And schematically, they have this form, the time derivative of the radius as this form, where A, B, and C are polynomial in this constant of motions. And for the angle, so you're using exactly as in Newtonian physics, you are on a plane, and you use r and theta to describe the motion. Sorry, r and phi to describe the motion. And this is also like that, with A, B, C, D polynomials in this constant of motion. Okay, and the tricky bit are these terms, which are those that differ from the, well, also inside this constant, but let's say the complication arises from these additional 1 over r cubed terms. But you can get rid of them through coordinate transformation, and in the end, you can bring the equation in a way. Sorry, I have to lose things. Okay. You can bring with the coordinate. So this coordinate transformation brings this equation in a form that can be solved analytically in a way that is very, very similar to the usual Kepler orbit. But of course, you have different parameters. Okay? The parameters are, if you want, the Newtonian one, plus others or correction, okay? So this can be solved. And for instance, if you have, if you ask yourself, okay, what does it change from the Newtonian problem? Well, the short story is that you have the Kepler motion, or a Kepler type of motion, so elliptical orbit with certain parameter, plus gas, plus the precession, okay, that you know from Schwarzschild, for example. This is what you get. And just to be a bit more concrete, one of the key results of this calculation is that if you calculate the periastron advance, what you get, so this would be the derivative of the periastron position. So this is the orbital element that identifies the periastron, averaged over one orbit. So this quantity has this expression. Okay, that's very interesting because from the Alsen-Taylor pulsar, we measure this. We measure this. Sorry, this is the eccentricity, which we measure. This is the period of the orbit, which we measure from the pulsar. This we measure as well, so we can get the mass. So for the pulsar, we can say that the mass, which is M1 plus M2, is about 2.8 solar masses. Okay. So this is an important result in post-Newtonian theory to understand the Nobel Prize observation. Okay, let me mention briefly how one does these things systematically and what are the problems. So to do these things systematically, we remember from day one that we could write Einstein equation in relaxed form. So this was the flat box in this strange variable, which is not a tensor, that is 16 pi g over c fourth minus g t mu nu, the Landau Lifshitz tensor, we call it tau, I think, and this other part, which is divergence free due to the gauge. Okay, so if you remember the first state, these are the full nonlinear Einstein equation in this particular variable, which looks like the flat box equals something, and the trick was to hide the nonlinear part in these two pieces at the right-hand side, okay? So, and this is harmonic gauge. And so to tackle the problem, one would really start from here, and one would assume a Pn expansion of H. So I will say that H is something like epsilon to the first power, a first term, then epsilon to the second power times the second correction, and so on and so forth. And okay, it was here. So we had solved the first iteration, right, where we just add eta, where we plugged in eta everywhere. At each order, so at given order n, the type of equation that you find are of this type. The correction of order n of this big H is given by 16 pi g. Let's call all of this just tau, so that the tau are the order n minus 4 plus the time derivative of the correction to orderless. Why? Because again, as we mentioned before, what we are essentially doing in this expansion is to forget or to expand in the retardation effect. Okay, so the retardation effects are small. And now if you look at this type of equation, it's a kind of Poisson equation, okay? And so you say, okay, I know the green function, I use I use my the thing that I learned in electromagnetism and I go through it. Well, no, the answer is no. You cannot do that because now this tau, because now this tau contains H at lower order. In general, you cannot expect that this tau has a compact support. Okay? It will contain metric pieces, and these metric pieces are all over. So in general, this source, this right-hand side of the Poisson equation, is not compact in space. If it's not compact in space, and you still try, and you still use the Poisson integral, these integrals are divergent. Okay, but there's not a problem here because you should not use those integral when you don't have when you have such an equation. So the usual green solution that you know, it's not applicable here. Okay. And the key issue, there's a deeper, okay. The key issue is this one. What we are doing here is essentially expanding in a function of the retarded time in this way. F of t minus r over c f of t dot plus 1/2 r squared c squared f double t dot and so on. Okay. But we have already argued that this expansion is a near zone expansion. It's not valid far away from the source. You have to stay close to the source. So in particular, you don't have such a, you cannot extend it overall. And one way to see it is that you can take the Fourier transform of that. So let me take This is exactly the same argument that we did day one for the quadrupole formula, but it's good to repeat it now. If you take the Fourier transform, this is a f of, so every time derivative here is a multiplication by omega, the frequency, the characteristic frequency of the source. And so you have such terms. And so on. And you see that here, what appears is the length. So this would be r divided by lambda square, if you now write omega over c, okay? And so this expansion here, of course, it's valid only if r over lambda is much less than 1, which means that r has to be much smaller than lambda. That is what I wrote here. So the type of assumption that we are doing is good only nearby, and it's fine, because there it's the place where we forget about the propagation effect of gravity. So, how to solve the problem? There are various proposals. Blanchet d'Amour have made the following proposal, which to my knowledge is the thing that actually have worked so far to every order. The proposal is the following. We keep the Hamiltonian solution nearby the source, but far away the source we use another expansion. And in particular, far away, so outside the source, and let's say end to the wave zone, use something that is called a post-Minkowskian expansion, which, as the name says, instead of expanding in epsilon, h will be expanded in g. So now I put the order on the other side. So the first iteration of this we have done. It's the Minkowski. And then you go ahead, you plug Minkowski and you solve, okay? 2, we solve inside the source. And in the near zone, so immediately outside the source, but already in vacuum, use the thing above, the post-Newtonian expansion. And the third step is that now we have to match these solutions. The reason is that this does not extend outside, but also this does not extend inside. Because you can think as a multipolar expansion, so it's 1 over r, 1 over r, and so on. So this does not extend, go down to 0. So the step is to match the two solutions in an overlapping zone that you assume exists. And it's precisely the piece of this that is outside the source, and it's the piece of this that is. So if you think about some radial thing, here you might have a source with the characteristic radius r. The number 2, so the post-Newtonian expansion would be here, up to some radius here that let me call it r out. which is much smaller than the length of the radiation. Then, so here I will use this type of expansion. Then, so this is the near zone. Then I will go to the wave zone here. And solve in post-Minkowskian, and I go down as much as I can. Say I go down here to R in. Okay, so wave zone reaches the wavelength of the radiation. And oops. And then I have this area here, I mean this region here, or assume that I have this region where I can do the matching of the solutions. Okay. And this turns out that it works, at least for those up to the order that has been calculated so far. And it is done with a technique that heavily rely on multipolar expansion. Okay, so you know multipolar expansion from electromagnetism. So it heavily relies on that. And in particular, what you find is that it's kind of always possible to do this. So if you start with a post-Minkowskian expansion, you solve it in you solve this H in terms of multiples. You need a finite number of multiples to match the post-Newtonian, the multipolar post-Newtonian expansion that you have from below. So you can do it. So at every order consistently. This is what they proved. And there is one thing that it's different from probably what many of you have seen in terms of this multipolar expansion. These are not multipolar expansion in terms of described in the usual spherical harmonic type of expansion. Okay? It is an equivalent, but somehow more powerful way to do this multipolar expansion that uses Cartesian coordinate, and Cartesian tensors, and in particular symmetric trace-free tensors. So what I want to try to tell you in the last half an hour is something perhaps a bit more mathematical. It is a bit of technique, an introduction to the technique that is used to solve Poisson and wave equations in this context, but also in the context of electromagnetism, for example. Yeah, so this is more or less what I wanted to tell you about PN. So now we switch a bit, slightly topic. And perhaps before starting this, these type of calculation have been pushed at very, very high order. So these have been pushed, some cases up to 5 PN orders. So these are really, and there are an infinite amount of details and calculation and complication that I've not talked about. How to actually solve the equation that comes out at every iteration. There are some techniques, and there are some issues and some techniques that solve this issue. When you apply this, so this is completely generic, but when you apply these things to, for instance, the problem of the binary system, this is rather complicated. It's simplified if you go on circular orbit. You have Kepler laws and so on. And that allows to push to push the calculation. When you have point particles, you have delta function, as we have seen. So you also need to discuss, on top of everything, how to regularize this delta function in the process of, and you need to do that, otherwise you don't get. So it's a big business, but it has been pushed, and it is continuously pushed by very few groups, actually. More recently, people have also joined the effort by using also other techniques like effective field theory techniques and so on. And this also seem to allow also to push this calculation, although at the moment they have mostly reproduced the existing result. Okay, from the solution of all of this, what one, for example, gets are this very long expression that every book and review, there is a very nice review of Blanchet, Living Review Relativity, which you should look at if you are interested in this. It explains all these things in detail. And you see there this long expression of the Lagrangian, this long expression of the Hamiltonian. You can calculate the energy correction at a very high order. And typically, what you do after you have all this result is, for example, you could still use energy balance equation, and from that calculate directly waveform approximant and the phase of the waveform in frequency domain by using the stationary phase approximation in a way similar. I think you did it. I don't know if you did it during the tutorials, but is essentially that process that you may have done during the tutorial of calculating the waveform systematically at every order. And this is a way to construct the so-called Taylor approximant for gravitational wave, which can be used to a certain extent. But they cannot be used, for example, so this approach is vital information, but cannot be extended to the merger. So the first thing that we draw here, the very first day, with this waveform, with the merger, and so on and so forth, that is not predicted by post-Newtonian theory. So only the early part, so the inspiral waveform that you have discussed at the Newtonian level, there are more terms coming from this calculation, and that can be somehow improved and extended. But there's always at some point where the motion becomes higher frequency, higher velocity, in which these methods are breaking down, okay? Although they are needed because they are the building block of other methods that then are used to actually calculate the templates that are used for detection. Okay. This is a bit more technical aspect, but I think it has, so I'll try to keep it simple, but I think it has, it has some interesting aspects that I'm not sure if everyone knows them, and it's completely general. So it's really about how do we look for solution of Poisson and Box equation and D'Alembert equations in flat space-time. This is all what we need also for post-Newtonian theory, because using this relaxed Einstein equation, we always have flat box or flat Poisson, okay? So this method can be used for electromagnetism and as well post-Newtonian theory. So let's start from the Poisson field and the scalar Poisson. This is the simplest thing where we can do something, and we can do something quickly. So let's say you have this equation, and this you solve by inverting the Laplacian with the usual Green function, for example. Equation 1, okay? So just to remind you, where do the multipolar decomposition comes from? Where you go, you go to the exterior, where rho is 0, where the density is 0. And you look for a decaying solution, for example. So decay solution means at infinity, this solution is decaying. And there, if you look one of such solution, you find that solution of the form spherical harmonics r to the L plus 1, where L is any power, okay, any integer power. These are particular equation. These are, particular solution of the Laplacian operator, okay? Why? Well, the Laplacian has a, as I say, a radial part, let me write it this way, plus the angular momentum part. This is identical to physics 2, it's physics 2. So these are eigenfunction of this guy, and r to the L plus 1 turns out to be the right thing, such that this guy is identically 0. Okay? And so if these are particular solutions, the external solution or the exterior solution will be a combination of these guys with certain coefficient that I usually normalize by 2L plus 1, y ln r. Okay. So, and this holds for radii larger than outside the source. And then what you do, these coefficients are unspecified, but they can be defined by matching the external solution with the general one, okay? And so the matching is done by expanding 1 over r in spherical harmonics. This is what you find in the Jackson. You have sum over L, a term 2L plus 1 as usual, and then you have R prime. So I use the prime for, say, Y, and I use the unprime for the modulus of X. And then you have Y star of theta prime phi pi, and Y ln. And then what you do is to plug in this thing in equation 1, and you have a sum, an integral, and stuff inside. Okay, and the integral is on y, so the integral is on the prime quantity. If you plug in that stuff there and compare this, you can simply read off, since the integral is on the prime, what remains, there will be some, okay, integral on the prime or y quantity, and then quantities that do not depend on the variable integration variable, which is this and this, which are exactly this and this. And so you simply read off, let me write it here, you should simply read off that the QLM are defined as integral in the prime variable, which is y, r prime L, rho of r prime, theta prime, phi prime, the spherical harmonics. So these are the multiple of rho defined in terms of the spherical harmonics. Okay? This is the result that you know. And so it starts with the charge or the mass, and it goes on. There's another way to do that. The other way is to take 1 over x minus r, minus y, sorry, and expand it here, okay, found it, and expand it in Taylor series. So if you consider this a function of y, for example, this will be f of 0 plus, in Cartesian coordinate, derivative with respect to y calculated as 0 and other terms, okay? But this expansion can be written as 1 over x, or 1 over r, minus yi, derivative in xi, 1 over x, plus many others, which you can collect together as a sum over L, and I'm using the same L, but it's not, yeah, it's related, we will see. Y1, YL, derivative xi1, derivative xil of 1 over r. What you use here is essentially this property that so the derivative with respect to y is of x minus y calculated in 0 is nothing else that the derivative of x I with respect to xi of 1 over x. Okay, this is just a property. And so on all the others. So there is an alternative expansion in Cartesian coordinate of the same green function. Okay? And now let's look at this quantity here. So this quantity here, well, this is symmetric, okay? You can switch the indexes and still get the same because of derivative, and they are traceless. Traceless in the sense, so because there are indexes, we want to call them tensors, okay? And they are traceless in the sense that you pick any two indexes and you contract. You get 0. Well, you get the Laplacian of 1 over x, okay? But except in 0, this is 0. And this happens in general. If you have L of this, you can contract any two of the L, and you get the same property. Okay. So there is a way to express the green function as a combination of symmetric and traceless type of tensor that are given by this. But these are derivative of 1 over r. So the derivative of 1 over r, you can work them out. Now r is x. All the derivative of 1 over r, you can work them out systematically. Okay, this is the unit vector divided r squared, and so on and so forth. The generic formula, if you have n of those, if you have L of those, is this. Plus, minus. There's a double factorial, which means you skip every other, you do the factorial, but you skip every other. L plus 1, r to the L plus 1, the traceless and antisymmetric combination of the unit so you multiply all the unit vectors, then you symmetrize. These parentheses like this means you take the tensor, you symmetrize it, and then you remove the trace, okay? So for example, yeah, so this is what it means. So another way of, so now you can substitute that thing there because it's the same. And you find out that you can continue this guy 1 over x minus y, it's sum over L 2L minus 1 double factorial, L factorial, R prime, R prime to the L, R to the L plus 1. These are the moduli, the modulus, R prime is the modulus of y as before, and you have L of those, okay, so this is R. And then you have y, so you have n prime vector L that are the direction of this y, and then you have these combination here. And there's a multiplication here. And there's a key thing. Things like this, I don't think I have to prove it, but you can prove it, it's not difficult. Things like this, so this piece that I have scattered all around, so this piece is exactly as this is a particular solution of the Poisson equation, okay? So if you plug it in, you get an identity, okay? So effectively, this is just an alternative but Cartesian formulation of what we have done there. And so a linear combination of these will be a general solution. You can match it and so on. And another expression of the solution, let me try to write it here, is that sum over L to L minus 1 factorial factorial. Q, now you have quantity with indexes, with L indexes, which I'm going to define, and then you have this N, I, N, I, L, divided by R to the L plus 1, where Q, these are not the same Q, these are different Qs, but they are related because Q are these integrals in d3y of L prime, you can read them from here, of rho y n I1 IL. And you can take it symmetric and trace-free because this guy are multiplied by a symmetric and trace-free tensor, so you can take it also there, okay? So you have rewritten the same as above in terms of Cartesian tensors, but not generic Cartesian tensor, a special type of those, okay? So these are symmetric and trace-free tensor. And where is the connection? Well, the connection between the two is that obviously n, the unit vector, depends on theta and phi. So this is just another representation. But it turns out that this is a more fundamentally reducible representation of rotation than the spherical harmonics. In particular, and I'm running a bit short, so I'll skip this. In particular, the spherical harmonics YLM theta and phi are given by contraction of certain basis. A certain basis of Cartesian vector, which are 2L+1, so the same amount, but carry indexes, okay, carry Cartesian indexes, and the spherical harmonics are given by the contraction with the unit vector Okay, how do we use it? Well, the nice thing of this is that it's much, so this might seem more complicated for the Poisson. It is not. It is similarly complicated because it's just that we, perhaps, if we are studying on the Jackson, we are more familiar on this blackboard, but this is actually easier to derive yourself. So this is equally difficult, but when you have to move from the Poisson scalar to the wave scalar field and to the wave vector and tensor field, this can be generalized very, very easily. Whereas, spherical harmonics becomes a mess because you have to introduce vector spherical harmonics. Here you simply add indexes. Okay, that's why it is nice. And so for what we need now, the game is to, how do we generalize this, or how these things are generalized for general relativity? Well, we need two things. We need to generalize from the Poisson to the box, okay, because we have wave equation in general. And we need to generalize from scalar field to, say, vector fields and tensor fields. So let me briefly discuss how this can be done. And so let's do first this. So let's do the scalar wave equation. Before continuing, I don't want to carry around all these indexes. There's a nice notation that he used in this paper. Contraction like, so this is a contraction. Contraction like that are usually indicated taking this L and promoting to uppercase. Okay, so this is a notation that reminds a bit about Einstein notation, but so it includes Einstein notation, but it also includes the fact that this is an uppercase L. It means there are L indexes. So this will save us a lot of space. And for the scalar wave equation, well, we have box phi, say, equals some source. Then exactly as before, we know that the solution is given by the retarded thing. So now it's a function of u, the retarded time, and x minus y. And you can go again and see, okay, how about the exterior solution of the wave equation? The exterior solution, what do? We need to look for for particular solution of the box equals 0, okay? It turns out that function of this type are particular solution of the box equals 0. Again, it's the same thing as there, okay? You can verify that this works out. So these are harmonic function. The general derivative of harmonic function are also harmonic functions. And the general solution is the combination of all of this. So I think it should be clear that the general external solution could be expressed as a combination of derivative of this, let's say, harmonic function this way. Okay. So this is another way, or this is the STF way, or the external solution in terms of STF tensor. And the question is now how to match this, so how to specify this F, right, as we did there. So equation there, it's like equation 2. So where is it? Equation 1. So now it's equation, say 1 prime, which means compare 1 and 1 prime, okay? And then equation 2 prime, you have to compare with equation 2. So logically, they are the same, huh? And so we need to do this last step where we find these guys, okay? This has been done. It's not simple. Again, it's a work by Blanchet d'Amour in 1989. Scalar wave equation in this formalism. And it gives a nice result, which this F function are given, not surprising, but some integral of some rho of u. This is the non-surprising part. Here you have YL. So you have L time yi, okay? So this is kind of multiple. So according to what we have discussed so far, this is really in the right direction. So it is, again, very similar to this. It's almost this one, okay? Except that we have the retarded time. But there's another integral. The complication in this case is there's another integral here, which is an integral of variable z of a certain function that is called delta Lz that that enters this. That enters the retarded time. So in the case of the box equation, you still have a multipolar, you can still express everything in terms of multipolar expansion in Cartesian coordinate, in STF tensor. They're still of kind of that type. But the difference is, it turns out that you have an additional integral to perform. And this is a kind of average on physically on a retardation effect that happen inside the source. So physically, you have to take into account of propagation effects inside the source. But so this is the complication. But conceptually, it's identical to what is done there. Okay. And by the way, if you are far away from the source, this internal integral is less and less relevant. Okay. So this is nice, and the nice things of it is that it generalizes to vector and tensor. With just one thing to remember. So now I have electromagnetism, I have Maxwell. have Maxwell or linearize GR in a certain limit. And it's the same thing as above. So I can write it down immediately. Say the zero component of A naught will be given by that solution there, sum over L minus 1 to the L factorial, the derivative of these multiples of U divided by R, and this will be given by the J0 component, so the density of charges, exactly by this integral here, for free. That's done. How about the others? Well, the others are also similar, and they will be given by something like that. Each of the spatial component will be other multiples that I call G over R that will be also given, each of 3 of them, each of which will be given by an integral like that, okay? Where instead of rho, there will be the spatial component of Ji. Great, there's one problem. What's the problem here? Let me suggest. Why this is nice? This is nice because we are looking at a solution in terms of SFT, which are a reducible representation of the rotation, which is the symmetry of this operator, by the way. And so this is irreducible in all the indexes L because it's SFT, but this is an additional index. So there's one bit of thing that you have to do when you want to generalize, that is look at your quantum mechanics notes and understand how to decompose this guy in terms of irreducible SFT tensor, okay? And of course, this is possible. I'll spare you this. But the final solution, okay, has been, by the way, that has been found by, what was this one? I think it's the Moore and higher. This is in the 90s. I don't remember exactly when, but so the thing that you have to do here is to say, okay, I have something like that, right? I have the sum. Sorry, yeah. I have the sum. I have one angular momentum L, and I have 1, and I simply need to decompose it as this. As a sum of irreducible pieces that will be also SFT tensor. If you have a, yeah, if you have a two tensor, you know there's a symmetric part, there is a antisymmetric, a vector part, and then there's a scalar part. It's that, okay. So you do the generalization of that at every L, and to find the final solution in the nice framework, you have to. Sorry, 91, it's written here. You have to further reduce this thing, and you simply find other multiples, and you have to change a bit the names of the multiple if you want. But in that case, they all appear irreducible, and you're done. And you find that A and AI are expanded in terms of electric and magnetic moments, exactly equivalent to those that you would find in the Jackson book and electromagnetic theory. What's the advantage of all of this? Beside the fact that it can be easily generalized, which is not a trivial thing. Well, one of the advantages is that these solutions are directly given in terms of the time-varying source. This you never get if you do the usual thing where you go through the Helmholtz, you go through Fourier transforms, Helmholtz equations, then apply that formula is there for the Poisson equation, and then you get a nice solution, but it's all in frequency domain, and you don't understand what it is. So this is instead given directly as a solution in terms of the time-varying sources. Okay, so it's a very powerful thing. It's what we have done for the quadrupolar formula. Okay, that's how you extend the quadrupolar formula. So, for very briefly, for gravity, it's conceptually identical. Okay, so you have now your Einstein. Sorry, there's also one thing, beside this reduction, there's also another thing, there is gauge, which I don't have time to comment about, but you can reduce things using the gauge and using the conservation law, okay? So what you do for Einstein, it's the same. You start with box pi g over C4 T mu nu. So you can invert this, and you will have the 0 component that you treat initially in this way as a scalar. The 0I component, you treat it initially as Maxwell. And then you have the IJ component, which you will have here IJL, an expansion on IJL, okay? And then you go through the same story. So you go to irreducible basis if you want. You use the gauge, you impose the equation of motions, and you end up with long expression, but let me give you a hint of how they look like, because it's nice. You get, for example, 0, 0, that is given, let me just catch it without the factor, okay? 0I, this is sum, where is it here? Delta L minus 1, the derivative, the first derivative of the set of multiples that are reduced already, plus IIJK SIL minus 1 over R and del L minus 2, sorry, IJL minus 2 over R plus IKL k. So this is how they look. There's another epsilon here. It's written everywhere, but okay. So you have a structure like that, and you have expressed the most general. Just look at it in the book because it's a long expression and so on. But these, the funny thing, the nice thing of these, so these are time derivative, the first multiples and the multiple times derivative of first and second order. And so you have given the most general solution to the tensor wave equation in terms of a multipolar expansion, in which each multiple is the time-dependent multiple on the source, okay? And in terms of two sets of multiple, the mass and the current. And look at here. This is the first term of this, so L equal 2. This starts with no derivative. This has two indexes only, and this is your quadrupole. But this built-in, then is built. This expression built in the entire multipolar expansion, and there is no assumption of small velocity. I didn't ask small velocity anywhere. Okay. And so this is very powerful. It can be used in electromagnetism. It can be used in every theory that you are interested in that has box and nubs as well. And this is for the linear theory. If you want, this is on Minkowski. But we have seen that the post-Newtonian theory can be written as a sort of theory on Minkowski through the relaxed equation. So if in your in your T mu nu that enters these integrals, you plug in the active mass and the active current density, and whatever you have at that order of post-Newtonian approximation, then you can still use this formula, okay? And yeah, this is how it is done. And the matching is, the famous matching in this PN approach is done at this level by matching these multiples, okay? Okay, sorry for, went to go a bit long, but I'll see you later.